All right, hello everybody. Maybe Groundhog Day for me here. I get to do this lesson over again because I found out the hard way. This. I found the hard way that if I have YouTube videos playing in Google Chrome while I'm using Google Chrome to do the lesson, that the sound things interfere with each other. So it seems like you'll be able to hear the sound if I have them playing on Edge instead of Google Chrome. So here we go. So we're looking at interference in sound. And so we've talked about constructive and destructive interference in sound in the past with waves, like water waves can constructively and destructively interfere. Pulses on a spring can constructively and destructively interfere. And remember, constructive means they add up and get bigger. Destructive means the opposite amplitudes are combining to be less amplitude, sometimes zero amplitude. So we're gonna see that and hear that now in sound as well. So first, we need to figure out. We're going to look at interference in sound with tuning forks. So we need to first see how a tuning fork makes sound. Let's go to that video here. So this is a tuning fork shown with a strobe light. And so a strobe light, how it works is you just see little flashes. And so your brain will stitch that together into motion. So basically there's going to be a flash of light with the tuning fork here, and then the flashlight when the tuning fork's here, and then the flashlight when the tuning fork's there, and then so it stitches together to a little motion picture for you. Okay, so that it just slows the motion down. Basically, it shows the tuning fork is really doing this. It's just hard to see. So it's doing this. It's vibrating in and out. Okay, and we end up with compressions in the middle, where when they compress together. Smartboard's starting up here, so wow, look at that. Computer getting messed up because I was just starting the smartboard. But so we get compressions here, and we get rarefactions there, and I'll be able to write better in a second once the smartboard's running. And so on. Okay, so you get the idea. So here, if we look at an end view of this, if we had a compression made here and a rarefaction made there, then if you extend that out, this side's going to be a rarefaction, that side's going to be a compression all the way along. At the diagonals, we're going to have spots where we have compressions and rarefactions adding up. And so they are going to destructively interfere. And so let's think about what that would sound like. So destructive interference. So really the amplitudes are going to cancel out. And so we're going to have, spoiler alert here. We'll come back to it. Let's go listen to our for ourselves. Actually, the idea is we want to be able to predict this, right? So it's going to be very quiet. Do you need something, Chris? More scissors? Yeah, I have some here. All right, so let's hear this for ourselves. Looks like this. It sounds like this. This one here. Here we go. I'm not tricking you here. I'm not turning the volume up and down or anything like that. It's literally just what I hear. So I had the microphone at my ear. So you get to hear what I was hearing, basically. So as I rotate it, when I go to a diagonal, it's super quiet. Tuning fork still ringing the whole time. Just can't hear it on the diagonals because of destructive interference. So, like, I don't know about you, but the first time I heard that and saw that and understood that, I was kind of amazed by it. Like, that's kind of crazy that works so well. So my actual video that I have in my files is called Tuning Fork No Sound Heard at the Diagonals. Okay, and it's because of destructive interference. And so, yeah, the next step we can look at, remind ourselves if we have 2 point sources. And so when you have 2 point sources in spots where they arrive out of phase, there'll be destructive interference, and spots where they arrive in phase, there'll be constructive interference. So the next step is to try and do that, to see if sound does all the things that waves do, water waves do, right? And so speaker to speaker here, if we have them out of phase, then obviously this crest is going to add up with this trough and add up to nothing, and this trough is going to add with this crest and add to nothing. So we're going to end up with quiet spots, right? So let's hear constructive interference first. So this is just two speakers producing the exact same frequency with a program that I have, and those are in phase, and so there's no, you're not hearing any change in the volume at all. Again, no trickery going on here. You can trust me. Destructive interference. This is the one where the trickery you might think is going on, but it's really not. And so hear how quiet that gets when they're near each other, because one's producing a crest, the other's producing a trough, and they cancel out. The video that we started off the year with, I think it's pretty amazing that cancellation happens idea-wise in your brain as well. So this is physical sound waves traveling through air, canceling each other out, because literally they're one's an up and one's a down, and they're adding to nothing in the air, right? So picture the air pressure being 101.3 kilopascals, and then the sound wave makes it go to maybe 105, and then it makes it go, down. It makes it go like 3 up and 3 down, let's just say, right? And so the up and down push cancel out literally physically in the air with air pressure. The weird thing in the video from the beginning of the year is that if you had this sound playing with earbuds in your right in your ears, there's no chance for the high and low pressures to cancel out. Yet they do in your brain. Your brain is, I don't know like how that works. That seems really strange to me that happens. But yeah, so this is a video of mine on YouTube that's gotten a lot of comments from people around the world, basically saying like, "How'd you do this?" And I found it originally at a physics conference here in Ontario, the Ontario Association of Physics Teachers. Someone was showing this, and I was fascinated, and I went out and, of course, searched for a program that I could make specific tones on 2 different speakers, and then switch them and so on. My program is this one here. I don't know if it'll open right now. Yeah, it's having trouble opening with current version of Windows and whatnot, but it still works on. Yeah, you can actually start it with compatibility settings, and it might ask for a license. But anyways, I'm able to produce tones, and I can go in and I can set it to stereo, and I can set one to plus 440 and the other one to minus 440. Okay, so that's how I'm doing that. Looks like it would probably actually work right now for me. Anyways, but that's what I use to make the system or do the video sounds. Now this one is kind of neat too. So I'll show in the video here that I have 2 speakers set up in the room, and so this is really this situation, right, where we get a nodal line pattern. So areas of constructive and areas of destructive interference in throughout the room. And so let me just pause quick here. All right, I'm back. So this will, throughout the room, you're going to hear the microphone pick up the increases and decreases in volume, and the microphone picks it up better than my ears do. I'm not sure why that is. I don't know if it's because ears are funneling sound in more than just one precise spot, or if it's my brain interpreting things based on my 2 different microphones that I have on either side of my head. I don't know, but this is what it led to as a video. All right, I have a demonstration set up to show interference of sound waves. And so I've got 2 speakers set up. Got this one right here, that one over there. And I'm just going to start a sound program. And it plays 440 hertz frequency tones from each one. And they're in phase. It's a special program that I'm using. I'm going to start that up. And I'll show you. Right, so you can hear this one. You can actually start to hear, I just noticed, you actually start to hear the constructive and destructive interference even there. I didn't notice that last time I played this. You can hear this one. But as I'm bringing the microphone across, you hear it loud and quiet, and then loud again right away, actually. But that continues throughout the rest of the video. All right, here we go. I'm just going to go around the room quiet. And then I get to a spot of, and I'm moving in and out as well. So there's actually more than just nodal lines going on here, I think, because they're probably not perfectly in phase. The speakers aren't perfectly doing what they're supposed to do. So there's spots where if I'm further away, it picks up sound versus not, and so on. But there's definitely constructive and destructive interference going on, just whether or not it's stable or not, and nice nodal lines. You'll hear spot soon on the way back here, I think. I'm a little closer or further away or whatever. Little spot there. Hopefully you're picking it up on the video here. Going through nodal lines, areas of constructive and destructive interference, so quiet and loud. So just as a reminder, or maybe a clarification here, if you have in phase sounds being produced, then if you're at the same distance away from both speakers, then they would arrive in phase and you hear a loud spot. And if you're arriving, if you're at a spot where they happen to be arriving out of phase because of the difference in the path length, like it just takes, you're further along the pattern, so you end up in a spot where you have a crest and a trough. That's where those quiet spots are coming from, and you can hear it in the recording, in the microphone, what it's picking up. This one here is a two-dimension, or like a straight line standing wave.
In the neighborhood, every delivery.
Boy, oh boy. Let's see if I can. There it goes. Short enough ad. I don't mind it. All right. So this guy here, his little wave experiment. So he's got a speaker on each end of the system, and he's got spots where it's constructive and destructive interference marked out. So we'll just get to the point where we can hear the microphone going between the two speakers. It's quieter and louder. Now he's right at the other speaker there. It doesn't go as quiet. I think maybe his frequencies weren't being produced very, very precisely, maybe there or something. But it's the idea, and that picturing the two speakers facing one another. And so we have speaker here, and there's my speaker, I guess, and then speaker here, whatever. And so they're producing sound waves. Like one goes this way, and one goes, let's make this one red here. The one goes this way, and so on. And then where you're getting a standing wave going, you're going to have, this kind of a standing wave and ending up going on. So you're going to have nodes and antinodes all the way along. So the next step is to picture this being like a loud area, and this being a quiet area, and this being a loud area, and so on, right? So that happens. The microphone in the video picks it up. This is a demonstration I love to do in class, where it's called Rubens tube, resonance in flames, and this one, is this mine? Yeah, this is my video. So this is my apparatus that I made after seeing this at a physics conference somewhere. But you actually have I have a speaker on one end of this ductwork. I've drilled a bunch of holes, and I have propane being pumped into it from the system here at the school. And I just light it, and a whole bunch of little lighter flames come out. And then the sound wave that's setting up inside of the air column there, you can see the spots where there's constructive and destructive interference. You can see the standing wave. Hear it, and you can see the patterns. Lower frequencies produce a lot more air movement. Always gets people's attention. So the best is when you do this on a nice cold day, warm everybody up. The other video that I had to do with this, missing from my lesson here. Let me just go into my videos. Ribbons. I just don't have a copy of the one where we played music. So if you play music through it, you'll have spots where a standing wave sets up with different notes that the singer sings. So you're basically seeing the sound waves. then different style of music. So obviously you're getting a lot more nice sine wave patterns with something like classical like this. So there's less going on. The big high notes from a symphony, long hold notes. The one class I had a student that I knew liked Mariah Carey, All I Want for Christmas Is You, which is probably currently defrosting for the Christmas season right now, right? You see the memes about that where Mariah Carey's in an ice cube and defrosting for the upcoming season. He played that and it was good. A use of this is huge. This commercial here, I'll play it from GNC 2016. They were advertising their active noise cancellation system.
Listens. Bose microphones that hear engine noise, then counter it with the sound canceling frequency, which helps make the cabin so quiet you don't miss a thing.
Night, Dad.
Good night, kiddo. It's called active noise cancellation, and it's available in the new, meticulously crafted 2016 Sierra.
So, physics for the win for selling trucks, apparently, too. So how that works, of course, is you've got microphones that sense the road noise, like they said, and then it's going to produce the opposite wave pattern. And so if you think of that, how that would work, these two wave patterns would add to nothing. So these little speakers actually produce the exact opposite of the road noise. If the road noise didn't exist, you'd hear road noise, right? But because they have the road noise and the opposite of the road noise, they actually cancel out, just like the microphone picks up the cancellation of sound in the room. Right? So that's a pretty cool system. iPhones advertise that they have it as well. Supposedly microphones here pick up the sound waves and play the opposite and so on. Oh, I'm just going to pause here. There we go. We didn't have the names of the detention people in my video. But yeah, iPhones supposedly do that too. I don't really hear it. But so if you're keeping track of properties of sound and waves constructively and destructively interfere both on springs and water waves. And now with sound, yeah, we're seeing this as well, right? Tuning forks are quiet at the diagonals, super easy to do, a very natural thing happening. With special speakers and systems, I can do that as well. And active noise reduction in car systems and so on. And the only thing else I had was just something interesting, is that I found a way to make karaoke tracks using a program that often is used in education called Audacity. And you can produce the mirror image sound of the track and play them simultaneously. And it leads to destructive interference of the vocals because the vocals aren't stereo. Everything else is stereo, so they don't really cancel out because they have a different signal on the left and the right, and so things survive. But because the vocal track is the same on the left and the right, you end up producing an up version of it and a down version of it, or opposite versions of the vocal track. And so when you play them together, the vocal track disappears. And so it's just an old school or whatever, kind of a weird way to make karaoke tracks. And could have been $1 million app idea for me, I suppose, because there's apps now that make karaoke tracks, and I was doing this before those. So if I knew how to make an app and whatnot, I maybe could have started selling that app. Oh, and one other thing I mentioned before about the piezoelectric crystals, vibrations, and so on. And so you vibrate a crystal, it makes a voltage. And if you go the other way around, you put a voltage on a piezoelectric crystal, it actually will vibrate. And so they drive a vibration of a tiny little tuning fork with piezoelectric crystals putting voltage on it. So that's how a battery watch that's analog and has a second hand that ticks and so on. They drive the frequency of the seconds tick-tocking in your clock, if you will, with a tiny little tuning fork. And they can adjust the length of this tuning fork super precisely, like just shave off a tiny bit of metal and it'll change the frequency. So they tune it so that it vibrates at this exact frequency or as close as possible to this. And then because that's such a high frequency that's tuned, relatively close to that, 32,760 or 32,769 or whatever, when you work your way back down, this number is actually 2 to the power of a whole bunch of times. 2 to the 2 to the 4, 2 to the 6, and so on, all the way along. And it makes it so you can have a really, really accurate second counting off, second by second measurement. So this video describes all of that really nicely. There's a process called flip-flops But basically, it's all factors of 2. It was a pretty ingenious design that they came up with for how to make battery-powered watches super accurate. So that is it for that. There's your assignment to do with this. And yeah, let me know if you have any questions. Thanks for watching.